but I'm going to continue where I left off last time for a while and sort of get the qualitative picture of volumes of free manifolds and then the paradoxical decompositions. And there won't be any volumes until next time, but there'll be Margulis numbers today. Okay, so, right, and where we left off was we had proved Gromov's theorem, and I just thought I should mention, this is more things you can find in Thurston's notes, there are some important extensions of Gromov's theorem that have to deal with situations like manifolds with boundary, and there's this strong version of the theorem which is sort of important for the applications. So the strong version says that this is what Thurston calls the strict version of Gromov's theorem. So it says anytime that you have a map of non-zero degree, if you have equality in the Gromov inequality, then the map is actually homotopic to a covering map. It's locally in isometry. So if the volumes are preserved by the map, then it's isotopic to an isometry. And this is somewhat more complicated, maybe less complete in the notes. You have to. The issue is that we use the fact that we had a homotopy equivalence to construct a continuous map from the sphere at infinity to itself. And then to prove this, you drop that assumption. You just have a map, and all you get is a measurable map from the sphere at infinity to itself, which is also not that easy to construct, but he does it. And then he carries out the argument in that setting as well. And then there's a relative version. So the key point that we need from the relative version is that when you're doing Dane filling of a cusp on a manifold with finite volume that has cusps, the volume actually strictly decreases. Well, we almost had a proof of that this morning. This is, I guess, the general version of that. Oh, that's nice. That happened before. What was what's the secret to this?
Two manifolds with the same volume. Right, so what does that say? Does that say there's
If you have a degree 1 map between them, then it's going to be isotopic, or homotopic to an isometry.
There's a common cover? Does it say something like that?
No, it says they're isometric. Okay, so moving on to Margulis numbers, I guess the starting, well, actually before we get to Margulis, the Margulis lemma, I want to discuss that, and I need a definition. So I need to think about isometries of hyperbolic space that move a given point x an amount epsilon. So I'll write it like this, kind of like a stabilizer, but it's only the epsilon stabilizer. And then the special case of Margulis lemma that applies to the case of hyperbolic free manifolds would say that there's a certain positive constant, I should have said it's positive, with the property that anytime you have a discrete group of isometries of hyperbolic space, which is generated by elements that move that point less than this magic number epsilon naught, then the group is going to be virtually nilpotent. So, I mean, this applies in much more general context. But for us, when we're looking at torsion-free groups of isometries that are associated with manifolds, the virtually nilpotent groups are just abelian, and there are 3 possibilities for them. You can have cyclic groups acting with a common axis, or you could have parabolic groups, which could either be cyclic or z plus z for abelian of rank 2. And the middle case of cyclic parabolic groups also won't come up for the finite volume 3 manifolds. Okay, so
Can
on
you show
that
us,
question,
just to slow you down, can you show us,
Thanks.
just to slow you down, can you show us that they actually have points which are moved randomly? Where are these points?
well, if you have, first of all, if you look at all translations along an axis, then you can move points, you can translate by an arbitrarily small amount. So do the upper half
But not
space
if I'm
model.
already in a discrete group and there's a minimum amount.
Well, if I just take one isometry, that's a discrete group that it generates. So I could take multiplication by epsilon on the upper half space. And that would translate along the vertical axis by an arbitrarily small amount. And similarly with the parabolics, if you take points that are, the translation distance by a parabolic, you take the hyperbolic distance, which is roughly going to be 1 over t, where t is the height, times the Euclidean translation, not quite, but more or less. And so those move points arbitrarily small amounts as well. I mean, it's the statement that those cusps diameters decrease exponentially is equivalent to saying that if you go far enough up towards infinity, you'll find points that move arbitrarily small amounts.
If I understand Gregor's question correctly, tell me if this is wrong. I think you were asking if there exist very, very short geodesics in finite volume manifold. Translate, if this occurs in the context of a finite group where the quotient manifold is finite volume, the answer is yes. I mean, you can't have this sort of thing where you have a very, very short geodesic in a non-complementary closed manifold.
Well, specifically, if you're looking at a fixed manifold with finite volume and you're doing different Dane surgeries on one of it, Dane fillings of one of its cusps, the manifolds that you get as the filling coefficients go to infinity approach the cusp hyperbolic manifold in the geometric topology. And there you have, if you go close enough to the cusp, you'll have geodesic loops that are arbitrarily short. And so these geodesics that you see at the core of the Dane filling will be arbitrarily short. So yeah, that happens.
So, how small or big is this Margulies constant?
Yeah, good question. I'll get there.
Oh, okay.
But so this is just qualitative at the moment. And I mean, let's see if we can go forward this time. Oh, I have to point this at that. There we go. Okay, so you can make this definition. You define the epsilon thin part of a manifold to be all the points in the manifold where there's a geodesic loop of length less than epsilon. That's not a closed geodesic I'm talking about. It's a broken geodesic. It's a loop starting at the point, coming back to the point, making some angle at the point. So anyway, that set you can call the thin part, and then the complement of the set you can call the thick part. And I guess I'm taking the thin part to be closed, which is supposed to be suggested by that half-open interval notation there. And the thick part is the complement, which is open. And then we can write down what the structure of the thin part is, assuming that we're taking an epsilon which is less than this Margulies constant. So if you make this definition, you can, well, I guess this is what we were just talking about, for a given isometry and okay. I want to define this C sub epsilon of a group, I guess. So C sub epsilon of a group is the characteristic set of the group would be all the points in hyperbolic space that are moved less than epsilon by some element of the group. So if you want to describe the thin set, you can do it by saying that it is the quotient of this C sub epsilon of whatever the group is generated by those short loops by the action of that group. How does this do that? Okay, so what do these thin parts look like? Well, there are these two cases. You can have a group of translations along a geodesic cyclic group where the translation length is very short. And if you look at all the points in hyperbolic space that are moved less than distance epsilon by that translation, well, it could be empty, of course, if epsilon is less than the minimal translation length. But if it's not empty, it's a banana. I guess I should draw a picture of a banana. In the upper half space model, a banana looks like a cone. So this is the set of all points in upper half space that are a fixed distance or less away from the vertical axis. But if you didn't put one of the ends at infinity, you would get some thing shaped more like this. It looks like this in the upper half space model, but that's actually an honest cylinder of radius r in hyperbolic space. And then the other possibility is you have a parabolic group that's your g, and then the set of points moved less than a distance epsilon by elements of the parabolic group would be the quotient, well, it would be a horoball, and then you'd be forming the quotient of the horoball by that parabolic group, which in the case of finite volume manifolds would be what we've been calling a cusp neighborhood lately. Yeah, question. Not exactly, no. I mean, Margulis numbers exist in higher dimensions, and you can talk about the thin part and so on. But parabolic subgroups can be more complicated. So, I mean, it's fairly specific to Freeman, but not completely.
You just, that banana is Earth, right? Is that related to your epsilon?
Well, so, I mean, if you look at, if you're asking, if you take a point on the boundary of this banana, and you know that the translation distance along the axis is such and such, and there's a certain rotation, then you can compute the distance, maybe it rotates to the back. You can compute the hyperbolic distance from this point to its image, and that's going to increase monotonically as you go further away from the axis. So as you move away from the axis, you'll eventually get to a point where your translation distance is equal to epsilon, the epsilon thin part, and that would be the boundary of the epsilon thin part. Okay, so the upshot is that the thin part, as long as you choose epsilon less than this Margulis constant anyway, which I mean wasn't really a constant. This is what Stavros was asking about, but there exists some constant that works for this. Then what you get for the thin part is some collection of tubes around short geodesics, which are quotients of the banana under the cyclic group, and cusp neighborhoods, which are quotients of the horoball under the z plus c subgroup. So this is in the finite volume case. The thin part will be union of cusp neighborhoods and tubes. And they'll be disjoint, although you could, for a given manifold, as we'll see later on, you could try increasing epsilon, which would enlarge the cusp neighborhoods, and it would enlarge the radius of the tube until at some point they would bump into each other somewhere. That would be sort of the biggest value of epsilon you could use for this. Yeah.
Can we see the statement of dilemma again, please?
Okay. To go all the way back. There we go. So we're starting with a discrete group, which is the fundamental group of the manifold. And within that, you're looking at a subgroup, which is generated by elements that move some point a very short distance. And the statement is that group is going to be abelian in the case of the finite volume manifold.
So how can I have more than one loxodromic isometry? You said it's a union of cusp neighborhoods and...
Well, there could be loxodromic isometries with completely different axes that project down to disjoint.
but they would generate in the medium group?
No, each one separately. So that the group of,
This seems to be saying the group has to be unique and generate by just one thing or maybe
Yeah.
two.
but I'm not saying how many of them there are. And I'm not saying that if I take an element which moves point X a really short distance and another element which moves point Y a really short distance, that those two generate an abelian group. It's elements which you fix one point and you look at everything in the group. You look at these short loops spaced at that point and take the group that they generate. That's going to be abelian. So if I have two short geodesics very far apart, then I have to pick a point on one or the other to describe this abelian.
But they are both in gamma x of epsilon 0.
X is 1 point.
Oh,
X is
X.
one
Oh,
point.
okay. Yeah. Thank you. I'm sorry.
Thank you. Yeah.
How does a banana look like downstairs? I mean, the cusp downstairs looks like, we've seen pictures of it, but how does a banana look?
You want to embed it in R3. The pseudosphere, you could imagine embedding in R3, I guess, for a surface. And I guess you could embed if you're willing to do 2 dimensions, then what you'd see is an annulus, which is very long and has a very tiny waist. That's the quotient of the 2-dimensional cylinder. And it looks topologically like a product, S1 cross D2. It's got a very short S1. And in general, you could have a very long D2 before it bumps into itself. Okay, so the next ingredient is this theorem of Girgensons, which gets very close to giving a complete picture of volumes in a sense. So this says that if you fix a constant and you look at all the finite volume 3 manifolds, hyperbolic 3 manifolds that have volume less than that constant, then they're all obtained by Bain filling a manifold on some finite list. So in other words, all those manifolds which appear on the list of manifolds with volume less than C, if you remove their thin parts, you're going to see the thick parts. There are only going to be finitely many thick parts that appear. And then you can get the manifold back from its thick part by doing Dane filling on some of the cusps. So I sketched the argument here. The idea is that when you're looking at the thick part, you have the fact that if you take any point in the thick part and you look at its geometric neighborhood of radius epsilon, that's actually an embedded ball. Points, the epsilon ball upstairs in hyperbolic space will embed in the manifold, because if it hit itself, then there would be a loop based at that point of length less than epsilon. So you could start packing epsilon balls into the thick part as far as you can, but you can only put finitely many in there because the volume is less than this number C. And when you're done doing that, then I guess one approach is you can construct from that a cell decomposition of the thick part using the Delaunay construction, which would say that you define a simplex to be a sphere which has no points from this finite set in its interior and has at least 4 of them on the boundary. Sometimes you might have more than 4. That gives you a cell decomposition, but the number of cells you have is finite, and so there are only finitely many ways that you can patch those together and get a manifold topologically. So that will be a sketch of that. Then we need a little bit more information, which I guess we don't exactly find in chapter 6 of Thurston's notes. You have to go to another part, but basically he proves the hyperbolic Dane filling theorem. And what that says is that if you fix a cusp and you look at a finite volume manifold at the cusp, you look at all possible Dane fillings of that cusp, he proves that all but finitely many of them are actually giving you hyperbolic manifolds, and he gives the construction of the metric. And those, the representations that correspond to those hyperbolic manifolds cluster around the representation that gave you the hyperbolic structure on the cusp manifold. And the only cluster point is actually at that discrete faithful representation for the cusp manifold. So what you can deduce from this is that if you, we already know that the volume goes down, strictly down when you do a Dane filling. And this statement coming from the Dane filling theorem would say that for any epsilon distance away from the volume of the cusp manifold, there are only finitely many Dane fillings that will be volume less than that. So from this, we can conclude that if we take all the volumes of all the finite volume hyperbolic 3 manifolds and scatter them on the real line, then the set we get is a well-ordered subset, and there are only finitely many manifolds mapping to each particular volume. So the idea is, you imagine so to prove it's well-ordered, suppose you had a sequence of manifolds whose volumes were increasing that was infinitely long, then passing to a subsequence, they'd all be Dane fillings on one particular cusp manifold. And the first Dane filling on that manifold reduces the volume by some positive amount, and everything else has lower volume, and there are only finitely many possibilities for that, according to the Dane filling theorem. So the sequence is eventually constant, contradicting that it's decreasing.
So in this proof of finitely many possibilities, you dealt with these cusps. But what did you do at the bananas?
Well, the bananas are Dane fillings, so you remove the bananas. I just take the thick part, and I look at manifolds that I get by, so the thick part will have a certain number of torus boundary components, except I made it open, but if you took the closed
The bananas are also Dane fillings.
you can think of those as Dane fillings. You added a solid torus to the manifold.
Thank you.
I mean, the Gromov construction doesn't require hyperbolic Dane filling. It's a topological statement. So if you glue on a solid torus and then get a hyperbolic manifold by doing that, you will have reduced the volume.
And this applies in this case also. This volume business.
Yeah. So these are the manifolds you're looking at in this sequence, for example, are going to be all obtained by adding solid tori to torus boundary components of one hyperbolic manifold closed up, or one manifold with torus boundary whose interior is hyperbolic.
Are there examples now when you do surgery that the volumes bob up like that?
I don't think so. Are there, Jessica?
I know of.
What's the question?
I mean, you have to decide when is one pair of integers bigger than another one, I guess. But, I mean, so even, I think, my understanding is if you just look at, say, 1 over n surgeries, that nobody knows an example where the volumes bounce around. But I don't know that that's a theorem. So the question was, do they, as you do bigger and bigger fillings, do you see things go bouncing up and down? So you could say travel out along the line, I guess, and z plus c, and look at all those fillings. I think empirically, yeah, they go down.
Well, there are bounds so that if you're far enough out and then go towards infinity, it will stay.
Yeah, so,
And Jessica will also talk about a different set of methods.
There's no single.
well, I mean, and in your setting that you were talking about, when you have this local maximum, I guess there you're seeing things will be decreasing when you're close enough to the vertical.
Doesn't that follow from the asymptotic expansions of the volume?
Well, it follows the end something. But you want to know
Can you just say again which Gauss theorem is this?
Well, the theorem, what I mean here is the theorem that says that when you do a Dane filling, the volume strictly decreases. So if you take a finite volume manifold and you glue a solid torus to one of its cusps, then you get a hyperbolic manifold that will have strictly lower volume. So that uses the relative version of Fromm's inequality, which I didn't do.
I just have a question about the argument. You said by passing to a subsequence, you can assume that there are Dane surgeries on a single manifold, single cusp.
Because there are only finitely many thick parts that appear in the sequence. So, right, so that's where Girgensons theorem gets used. Okay, well, so if we know this, then it makes sense to ask the following kind of question. I have some property of hyperbolic 3 manifolds. The hyperbolic 3 manifolds are a well-ordered set, so you can ask, all right, what's the first manifold that has that property? So there are results along these lines. If you take the property to be M is non-compact, orientable, there was an answer found to this by a result of Kyle and Meyerhoff. In other words, the smallest volume cusp hyperbolic manifold was discovered. And they also found number 2 on the list. And then more recently, this work of Gappai, Meyerhoff, and Billy gives you the first 10, which turn out to be the first 10 manifolds on the list that came with this mysterious program, Snappy, long ago when you could get it. So, I mean, those were found by doing a combinatorial search through all possible ways that you could glue together up to 7 tetrahedra and end up with a manifold, and then finding the volumes on the ones that were hyperbolic. And we now know there aren't any more besides that. So the first 10 are known, and they were also able to answer the question for closed and orientable, find the first manifold on the list, which is closed and orientable, which was the first manifold on Jeff Weeks' list of closed orientable manifolds, therefore called the Weeks manifold. And it has this surgery description, -3,1 surgery on that mysterious sister of figure 8 that came up the other day, and it has volume 0.94.
So,
This is a proof by rigorous computation and math as well.
so, and this is independent of estimating the Margulis constant?
Yep, they don't estimate the Margulis constant. Whatever that is. So maybe I can give the definition now. So you could make this definition. If you have just one manifold, then you can ask, well, how thin do you have to make its thin part before it looks like it's supposed to look, namely a union of cusps and cusp neighborhoods and tubes around geodesics. And so you could say that a number, epsilon, is a Margulis number for that particular manifold if it has that property. The thin part looks standard. Or you could do the same thing for a family of hyperbolic manifolds. You could say then the Margulis constant of the family would be the largest value that serves as a Margulis number for everything in the family. So guess that's what we mean when we say the Margulis constant would be the Margulis constant for some family. Of course, you might take all closed hyperbolic manifolds or cusp hyperbolic manifolds or both, and so on. But yeah, one point is that that number for just one manifold, the smallest epsilon, or sorry, the biggest epsilon with the property that its epsilon thin part is standard, is a topological invariant of the manifold by Mostow rigidity, because every geometric property is a topological invariant according to that. And so it's, as reasonable one to look at as the volume. But to answer Stavros' question, the Margulis constant, let's say, for closed manifolds is not known. And there is a bound due to Meyerhoff, this number 0.107. And my experiments indicated that if you took Week's manifold as your guess for what would be the kind of extremal case, who knows, but then you would get a number that's more like 0.774, so possibly this estimate is not all that accurate yet. And it's been around quite a while, so there's not too much known at this point.
Can it be lower for custom manifolds?
Can it be lower for cusp manifolds? I guess, as far as I know, it could. It would be kind of strange, but yeah.
So there's no theorem.
Yeah, I don't think there's much to know at this point. I did want to mention another theorem, though. Is that on here? Yes. Peter Shalin has a recent theorem that shows that this number, 0.3925, is a Margulis number for a manifold, closed manifold, under arithmetic assumptions. So if you assume that the trace field is a quadratic field, and that the group has integral traces, and you rule out some small torsion in the homology, then there's a larger estimate than the best known for that class. Okay, so I guess we'll get to the point here in a second, but here's a theorem which is purely a theorem in three-manifold topology. It does not have any hyperbolic geometry in it, but it magically has hypotheses that are exactly satisfied for all closed hyperbolic three-manifolds. It's due to Westjaco and Peter Shalin. It says that if you have a closed, irreducible hyperbolic three-manifold, and there's no Z plus Z subgroup in the fundamental group, then any two-generator subgroup of infinite index is a free group. So the proof uses the compact core theorem, and it uses a homology computation. And basically, you're proving that when you take the covering space corresponding to this two-generator group, it's a genus 2 handle body. So one thing you can deduce from this theorem then is that the closed hyperbolic three manifolds fall into two camps. On the one hand, you have manifolds which have a finite cover that has a two-generator fundamental group. Since if it's not the case that every two-generator subgroup has infinite index, there'll be some two-generator subgroup of finite index, and that will give you a two-generator covering space. Otherwise, the sort of big case, any two-generator subgroup of a closed hyperbolic three-manifold that's in class 2 is going to be a free group. So the log 3 theorem that I want to talk about is basically an estimate for the Margulis constant for the bigger class, for the manifolds that have the property that all two-generator subgroups are free. And the family of two-generator Kleinian groups is, in some sense, manageable. It's kind of been proved to be manageable because the theorem that I quoted of Gabai, Meyerhoff, and Milley, that involves a computer search through the entire space of these groups, which is, their groups are described by 3 complex parameters. If you have a 2-generator group of isometries, let's say loxodromic isometries, then each one has an axis, and it translates and rotates along its axis by some amount given by a complex number, and the other axis has a complex translation, and then the 2 axes themselves have a complex number that describes the translation of an isometry that would shift one to the other along their common perpendicular. And it's a bounded set inside that 3-dimensional space. And a computer has at least gone through that bounded set and answered some question about all of them. So maybe you could imagine that the 2-generator ones could be classified or understood computationally. So that leaves the other class, the ones where all the 2-generator subgroups that you see are always free. Oh, and I guess it's also widely believed that any closed hyperbolic 3-manifold with a 2-generator fundamental group would have a genus 2 Haggard splitting. And genus 2 Haggard splittings are sort of classified. So in some sense, there may be hope for classifying 2-generator manifolds. Question? Okay, so here's the theorem I was talking about. So we're in a situation where all 2-generator subgroups are free now. So let's just look at free groups. So we have a group of isometries of hyperbolic space. I'm thinking of it as a subgroup of a fundamental group of a closed hyperbolic 3-manifold, so it won't have any parabolic elements. So let's assume that. Then the theorem says that if you take any point in hyperbolic space, one of the 2 generators will have to translate that point a distance at least log 3. Or in other words, log 3 is a Margulis number for the closed manifold that contains this group. And there's a fancier version of this which is quite useful in all of the, it's kind of the basis for a large part of this estimates that we've done for volumes, so I'll state it here. You can consider an n-generator free group, and the statement that the larger of the 2 distances is greater than log 3 is qualitatively a little weaker than what's really true. What's really true is that if one of them moves a point a short distance, then the other one has to move it a long distance, longer than you would expect if they were both, so that the log 3 case is only sort of when they're both equal. And the general relationship is this equation, or inequality here, that if you add up 1 over 1 plus e to the distance the point gets moved by these different basis elements, the sum should be less than a half. So if one distance is short, making one of those terms large, then the other terms in the sum have to be small, so all the other distances will have to be small.
Is there a relation to Machine identity, or is that just coincidence?
I don't know if there's a relationship to McShane identity. I mean, it seems pretty clear there must be, right? But maybe it's coincidence. I don't know.
Is this a trace calculation? Simple trace formula calculation?
Well, not exactly, no. Well, you'll see what kind of calculation it is. I mean, it involves... Well, you'll see. There is an algebraic calculation in there. I'm not actually going to give the derivation of this formula, but it's, yeah, there is some algebra that may be the same algebra that you do with the traces, actually, yeah.
If I have gamma 1 and gamma 2, which are loxodromic, is it true that the group will be free even only if the axes are disjoint?
No, it's not that simple. Yeah, maybe I should probably should give at least one sort of typical example of what these free groups look like. So the typical example would be a Schottky group, a classical Schottky group, if you like. And the way you would describe those is you take 4 disjoint circles in the plane, and you look at, so I'm not drawing the axes now, but I'm looking on the sphere at infinity. You look at isometries that pair these circles up, x and y. And so actually what x is doing is it's taking the complement of this circle and mapping it into the interior of this one. So you can see, well, a lot of things here, like you take the plane minus these disks, that's a fundamental domain for the action on the plane, so the plane is giving you a genus 2 surface, which is the boundary of a genus 2 handle body, and you can iterate this map and see that with your x, you'll get 3 circles inside here, and inside there, and so on. You can see the kind of intersection of all those things as a Cantor set in the plane. This is your typical, maybe easy to understand free group of isometries. So what's qualitatively true is that if the translation lengths along the axes are really large, it doesn't matter whether they're disjoint or not, then the group will be one of these Schottky groups. But as you shorten the translation lengths, then, whereas if you deform this group in that way, just shortening the translation lengths of the elements, it remains a free group long after these spheres would bump into themselves, and you can continue it for a while using quasi-circles in place of the round circles and still be getting free groups of isometries. So it's a pretty complicated behavior. But what's true qualitatively is that for very long translations, it's going to be free. And the proof of that is just the ping pong lemma. Okay, so these statements that I'm writing down here are subtly much stronger than the ones that were in the original papers where these appeared. And also the proof is simpler. And the reason for that is that in the meantime, a lot of really important hard problems in the theory of finite groups have been solved that we were kind of stepping around and trying to do this. We'd step around it in 2 ways, add hypotheses and make the proof more complicated. So originally the hypotheses would say that the groups involved have to be topologically tame. Topologically tame means that the hyperbolic, so we've left this comfortable world of finite volume hyperbolic manifolds now, even though we're somehow interested in their volumes. But here you're talking about Kleinian groups which have infinite covolume and nastier behavior, and so you can still form the quotient, however, and you get maybe an open manifold, which would possibly be the interior of a bounded manifold. And that was the tameness conjecture, was that any discrete group of torsion-free discrete group of isometries, when you form the quotient manifold, it's actually the interior of a manifold with boundary. So that was recently proved by Agol and by Caligari and Abide independently. And another important result, which has been probably recently proved, maybe people aren't absolutely sure yet, so I left it out. But if I added that, the Bayes density conjecture, then I could drop this condition of no parabolics as well. Okay. Yeah, so now we can talk about the paradoxical decomposition. So the name comes from the von Arctarski paradox. Von Arctarski paradox ultimately rested on this property of a free group of rank 2, which is that you can divide the free group of rank 2 into 5 sets, the identity element by itself, and then all the words that start with x and all the words that start with y, and x inverse and y inverse. That's a decomposition of the group, but it's kind of behaves in a way that is surprising from some points of view. Like if you take all the words that start with, well, if you multiply on the left by x, is that the way I did this? Yes. So if you multiply on the left by x times the set of all words that start with x inverse, so you cancel off the first letter, and what you get is a word that starts either with x inverse or y inverse. So one of these four sets is mapping onto the union of the other three, which is also, pretty familiar from the usual picture of the free group of rank 2 acting on a tree. So your four sets are these subtrees here, and if you shift right by x, then it pulls all three of those things into one. So that led to this decomposition of the sphere into pieces that could be reassembled into something bigger. But that's kind of a fundamental property of the free group of rank 2. And, well, you can see this in terms of the action on the tree, but you can also see it, if you want, by looking at the ends of the tree, which would be a Cantor set. And the Cantor set divides up into these four disjoint pieces, and those pieces behave this way. One of them maps onto the other three. So the idea of the proof of the theorem, I have to give the definition, sorry. So you can do the analogous thing for Kleinian groups. You can talk about the limit set of the Kleinian group, which is, you think of any point in hyperbolic space, you take its orbit, and look at all the accumulation points of the orbit. Well, the orbit is discrete, but in the topology of the closed hyperbolic space, when you add the sphere at infinity, you can have accumulation on the sphere at infinity, and all those accumulation points are called the limit set. So that's the analog of the Cantor set for the tree. And so you would maybe expect that if you have this free group acting on hyperbolic space, you could decompose the sphere at infinity into four pieces which behave in this way. And that's basically true, except that as it happens in the argument anyway, it may actually be disjoint, but as it comes out, we have to use measures instead of subsets to decompose the sphere. Okay, so I guess I mentioned back here, I forgot to discuss this. When you define the limit set, I said you pick one point and you look at its orbit, take the accumulation points of that. But if you were to choose a different point and take the accumulation points of its orbit, you get the same set. That feature doesn't quite persist. So in our construction, when we're decomposing the sphere into measures, we're going to choose a point and do this decomposition, but what we get is going to depend on which point you picked, but it will depend on that in a very controlled way, which has been formalized by Dennis Sullivan as something called a conformal density of dimension D. So I thought I would give an example of a conformal density of dimension D. So it's the main example. It's called the visual, call it the visual conformal density. So what is it? For every point in hyperbolic space, it's a certain measure on the sphere of infinity. And the measure that it is what you would get by just taking the measure on the round unit tangent sphere at the point, the standard measure, and pushing it forward to the sphere at infinity. So it's going to vary as you go from one point to another. If the point is very close to one part of the sphere at infinity, then that part is going to play a much bigger role in the visual measure than the part that's far away from that point. So what you really get is some kind of family of measures, one for each point, but if you want to translate from one to the other, it's pretty simple to do. There's a specific function that you can write down. It depends on the point you're starting from and the point you're ending at. And we calling it P here. It's the Poisson kernel, actually. So it's a function on the sphere at infinity that depends on the choice of those 2 points. And you can go from one measure to the other by multiplying. So the integral of a function with respect to one measure is the integral of the function times this kernel with respect to the other measure. Or if you like, d nu z prime is this function squared, I should have said, times d nu z. I didn't want to write the function down, but I can sort of describe what it has to be. There it is. At least, if you want to say, what's the value of this function at one point, you could do it like this. You could put that one point at infinity in the upper half space model, and you could put your z and z prime, the 2 base points that you're comparing the measures at, on the z-axis. And then the isometry that moves one point to the other would just be multiplication by t. Put one point at height 1, the other one at height t. You'd be multiplying by t. And you're also expanding measure by a factor of t squared when you multiply by t. And so to compensate for that, the value of the function should be 1 over t. So that doesn't give you a formula, but that's kind of the construction of it. Okay, so let me describe the construction of the measures. So we have to start with something called the Micronase Series. You take a point in hyperbolic space and you look at its orbit under this group. And for every positive number s, you can write down this expression here. You sum up e to the minus s times the distance from your base point, where you're defining the measure, to each point in the orbit. So the basic idea is that this number s is supposed to be kind of measuring, or compared to the growth rate of the orbit, the number of points inside of the ball of radius r. So if s is larger than the growth rate, then this series is going to be dying off very quickly and it will converge, and if s is less than the growth rate, it will diverge. And there's this particular point in between called the critical exponent, where you don't know whether the series converges or diverges, but it splits the values of s into the 2 pieces. It turns out it's a lot easier to describe what happens in the case when it diverges, so we'll assume that. So I'm going to assume that this series diverges for a particular choice s equals d, and it is important that the d does not depend on which base point you're using. The critical exponent is independent of that. Okay, so how to construct the measures? Well, I'll choose some values of s where the series converges, and I'll just let them tend down towards the critical exponent. And then I construct the measure by just putting a Dirac mass at each point in the orbit and weighting it by one of the terms of the series. So the series is actually representing the sum of all those weights. So I divide by it to get something with mass, total mass 1. And then I want to take a limit as the s is decreased to the critical exponent. And you can do that in the world of weak limits, so it doesn't really, not giving a canonical construction necessarily, but just a measure that behaves correctly. So what happens when you do this, if you fix any particular ball in hyperbolic space, what's happening as the exponents go to the critical exponent is that the total mass inside that ball is converging to 0, but yet the measures are converging, so their support has to end up being on the sphere at infinity. So that gives some sort of measure on the sphere at infinity, and it's pretty formal to see that let's see, what am I saying? same series, the same sequence of measures, the same subsequence of S's is going to give convergence for any point that you pick. And these measures were constructed by putting little Dirac masses on all the points of the orbit. Well, the orbit breaks up into the 5 pieces, or 4 pieces, if you like. The ones that start with x, y, x inverse, and y inverse. So I've really, you can ignore the singleton, I've really broken up the measure into these 4 pieces that correspond to the masses positioned on those 4 subsets. And those measures will converge. And it's formal that this gives you something which transforms, not like multiplying by the p to the power 2 necessarily, but p to the power d instead. And key point is that if I look at what happens when I shift the base point by the element x, which is one of the generators of my group, it behaves just like the paradoxical decomposition. So what you get when you shift the base point for the x bar measure by the element x is you get the sum of the x bar measure, the y measure, and the y bar measures, which is the complement of the x measure, if you like. So that's one formula that you see directly because the sets are actually that are supporting these measures are actually the same. But on the other hand, the conformal density property gives you a second way of calculating what happens to the measure when you shift by x, which is namely that you integrate against this Poisson kernel to find the transformed measure. So the proof involves doing the calculation those 2 ways and seeing the result. So there is some algebra in there. I don't know if it's the same as you change it. Okay, so if I could hit the right button here.
So what is the result in what are we proving now?
Well, what I'm proving is that I can, given this free group of isometries, I can build a paradoxical decomposition of the sphere at infinity as, a measure theoretic one. So I have these 4 measures which transform in a certain way when I move the base point, and they also transform in a certain way given by the paradoxical decomposition because of the fact that they're constructed out of the orbit, which is a union of these 4 sets. So ultimately, what I want to do is argue that if you have such a decomposition, then the element x that I'm translating by here has to be pretty long. And the way that comes out in the computation is it has to move the point a pretty large distance, and explicitly log 3. And the way that works in the computation is that this function p, the Poisson kernel, it's sort of like a big spike near a certain point on the sphere at infinity. And if you're going to be able to integrate against this spiky thing over some set, which has a certain measure, and get a result which is sufficiently large, then the spike has to be tall, which means that the translation length has to be long. Okay, so I'm almost at the end here, but I have to race through a bunch of important terms. Yeah. We don't know if they're mutually singular. There have been, there's been some computations that suggest that they are, but we don't use that. So. Yeah, I think right. I think that's probably true that they're actually sets. Yeah, the D is very often, the D is exactly the Hausdorff dimension of the limit set. So the support of the measures is the limit set of the group in general. It's not, the example I gave, the support was the whole sphere, the visual measure, but this construction, what you're doing is you're taking limit points of the orbit, basically, on the sphere at infinity. So the support comes out to be the limit set of the group. And the Hausdorff dimension of that is D, usually. Okay, so I just want to now get a big sledgehammer and finish this off with theorems from Kleinian groups. But I have a whole bunch of them, a lot of sledgehammers. So let me just run through that. So first, where are we working? I mean, ultimately what we're trying to do is to do some optimization question over all groups in this family, all of these free Kleinian groups. So we should be working in some space of Kleinian groups, and the space, the first place to go would be just the representations. Each group appears as a representation of a free group into PSL2C, and we divide by conjugacy as usual. And as I mentioned, that's kind of a concrete thing given by three complex numbers, if you like. And then inside of that, you have the representations which are actually discrete and faithful. That's the set D, and it's a theorem of Chuck-Rowe that set is closed. And then within D, you have the Schottky groups, geometrically finite groups. So those are the ones that have the property, one definition is that they have a finite-sided fundamental polyhedron. And it's a theorem of Martin that that's an open set. So that's an important point, actually. You can see immediately that whatever this extreme group may be, it's not going to happen in the geometrically finite part, because geometrically finite being open means you can perturb the group in any direction in the space of representations and it will stay discrete and faithful. So it's very easy to change the complex parameters to reduce the distance that your point gets moved by some element, just shorten the element a little bit. So now, a big sledgehammer. It's been proved recently, or almost proved, that the closure of the geometrically finite groups is actually all discrete groups. It's known as the Baer's density conjecture. And it's an older theorem of Baer's that among the groups on the boundary, the ones with no parabolics are dense. So if we don't want to we want to rule out the parabolics, we can do that using this theorem. And also, not quite that old, but well-known theorem of de Canaries that was based on work by Francis, shows that if you look at a topologically tame group, it's also what's known as analytically tame, which means that there are no non-constant superharmonic gamma invariant functions. And then finally, the Martin tameness conjecture, Adol and Caligari and Ally. All the groups are topologically tame, so we can apply Canary's theorem to all of them. Originally, we had to exclude the possibility that they weren't. Okay, so here's the argument then. You're trying to minimize this maximum displacement over the whole group. We know that the minimum is not going to occur in the geometrically finite part. It has to occur on the boundary. And the groups we're interested in are dense on the boundary, so we may as well work with that dense set. So we can work with groups which have no parabolics, they're geometrically infinite, and they're topologically tame, according to the tameness conjecture. Those will all have limit set equal to the whole two-sphere. But if I take any d-dimensional conformal density, it determines an eigenfunction for the Laplacian with eigenvalue given by that formula, and it's positive, and that formula is negative, so that means it's a superharmonic function. So it has to be constant by Canary's theorem, and that means that the dimension has to be 2 in this case. And then you can prove that that actually means that the measure that we constructed for the whole group was the visual measure in the first place. So now what we're looking at, so one more trick, I guess. You don't really have to do this. And by not doing this, you get the stronger form of the theorem. But If we just kind of symmetrize everything as much as possible, we can assume that of these four measures, the ones corresponding to x and x inverse have the same mass. The ones corresponding to y and y inverse have the same mass. And let's say the one corresponding to x has mass less than or equal to a quarter. Then we calculate this change of variables under moving from z to z prime in two ways. And one way says that we should be able to integrate this Poisson kernel against a measure which has total mass a quarter and get out a measure which has total mass 1 minus a quarter or less or more. So that means that the Poisson kernel has to be large, measurably large. I mean, you can look at the worst case, which would be where all the mass that you're integrating over is concentrated in the part where the Poisson kernel function is as large as it can be, and it behaves monotonically. It's got a maximum that decays off from that. And then you have to do a calculation, and it turns out that if the Poisson kernel function is going to be that large, then it has to correspond to a displacement of at least log 3. So that finishes the argument. Questions?
Okay, let's take this break again. Next talk at 3:20.